Debería estar grabando ya.
Lo tendría que poner arriba.
Ah, ahí está.
Ok, no he dicho nada.
Okay, so welcome everybody to this quantum meeting. Today, Jose is going to talk about fluctuation theorems, both the role of imperfect detection and feedback. So the stage is yours.
So, hello everyone. As Gonzalo said, today I'm going to talk to you about just a formulation of the second law at the level of fluctuations in two different scenarios. One is in which we have like partial information about the state of the system, or we have imperfect monitoring of our system. And the second one is a little bit about work in progress in the case in which we have feedback and Maxwell demons setups. So I want to start with the imperfect detection part. Wait. No, nothing is working. Okay. Oh. So nowadays we are able to measure and manipulate smaller and smaller systems. And this up to some scales in these systems, if we want to study the thermodynamics, fluctuations become relevant. And also, in some of these systems, you will have quantum effects that you cannot neglect or that you don't want to neglect because they are important. For example, this is the case of light harvesting complexes, in which the energy of an excited photon is transferred to a reaction center in a coherent way. Also, for example, some quantum thermal machines experimental implementations, like the ones made by MB centers or trapped ions, or maybe some quantum electrodynamic experiments, like the one of Harosh here. So if we want to study these fluctuations, you will need some trajectories for your system. And in order to describe trajectories in quantum systems, you need two main ingredients. One is the two-point measurement scheme, defined as a predictive measure at the beginning and at the end of a given Dirac dissipative process. In this work, I want to center in measurements of generic observables and a system whose dynamics can be described by Markovian dynamics, normal assumptions. And the second ingredient is that you want to monitor the interaction of your system with the environment. That can be the case of having, for example, a cavity and putting a photodetector, and every time you hear a click here, it means that you have detected an emission of a photon. And then you can keep track of the number of photons that you have inside of the cavity, for example. So with these two ingredients, you can define what is known as a quantum trajectory. Here I'm going to focus on quantum jump trajectories. In this case, in this case, you have a Lindblad-Master equation describing the evolution of the system at the average level. And then you have some local detail balance between the Lindblad operators, ensuring your thermodynamic consistency of the equation. And then you can, by putting these two ingredients, you can unravel the evolution of the system at the level of trajectories, obtaining what is known as an stochastic master equation, stochastic master equation. Sorry. So now you will have an unitary evolution, smooth unitary evolution, as the one that you have in the Schrodinger equation, and then you will have a smooth non-unitary part, and also an abrupt change in the state of the system due to the happen of a jump. It means an interaction with with the environment, meaning that you have absorbed or emitted a quantum of energy. For example, imagine that you have a qubit in contact with a thermal bath and you're having some Rabi oscillations here. And then your evolution in the Bloch sphere is going to be like something like this. And then at a certain time, you emit a photon. It means that you decay to the ground state of the system. So here, the smooth evolution is going to be like this blue part. And then you have the jump, which is this instantaneously change of the state of the system. So taking this into account, you have that the trajectory of the system is described by a measurement record. That is going to be the initial and the final state of the system, described by the 2-point measurement scheme, and then a set of jumps that are composed by the channel that the type of the jump that you have, because you can have different jumps in your system, and also the time at which the jump happens. So a good point to start to study the thermodynamics of the system is to define the stochastic entropy production. That is defined by the log ratio probability of the probabilities between the forward trajectory, I mean a normal trajectory in your system, and the time reverse trajectory, defined as the trajectory in which we invert the driving of the system. So, and also it can be shown that this stochastic entropy production is going to coincide with the thermodynamic entropy production of the system. That for a trajectory is going to be composed by two terms. One is the system entropy, which is just the change in the surprisal. So it is completely defined by the 2-point measurement scheme. And the average of the system entropy is just the von Neumann entropy. And also you will have some entropy flow. That is just the heat that you have exchanged with the environment during the trajectory. So this, so far so on, this is more or less just thermodynamics of quantum trajectories with total information. If you want to see more into detail of all of this, here you have present review on the topic. And now a question is, what happens if we cannot detect all the jumps? Or to see, in other words, if we cannot see all the channels. For example, imagine that we have an atom-level atom inside of a cavity, and then we have some external driving, and we have a detector. So we will have detected emission, but we can have hidden absorption, for example, because we cannot see when the atom absorbs a quantum of energy. Or maybe you can also have hidden emission because you have some errors, or this emission is associated with another channel, whatever. So in this case, you can see that now the evolution of the system conditioned to the record is going to have another another part that is described as smooth evolution in the Hilbert space, but now it's associated with the hidden dissipation. No? So now the question is, can we still formulate the second law at the level of fluctuations in this setup? This is the problem that we try to solve in this paper here, with some collaborators from the FISC, Marc Ferri, myself, Rosa Lopez, Roberta Sambrini, and Gonzalo Manzano. The key point here is that we can split the monitoring record in two parts. One is a visible trajectory, is the trajectory that your detector is going to show you, and the other part are like hidden jumps, that are the jumps that happens, but you cannot see. So what can we say about dissipation only by taking into account the visible part of the trajectory? Okay. For this, we have to define the conditional entropy production of the system. It's going to be the entropy production defined as previously, but only taking into account the conditional heat, that is the heat that you see, And here the conditional average are defined in this way just over in which we average over the hidden part of the trajectories. For example, here I show you this two-level atom inside of a cavity for a given observed trajectory, which is having two visible jumps at a given time. And then in the color lines, you can see all possible trajectories that are compatible with having these two jumps. Okay. And now, now I'm going to define this. We're going to define this irreversibility estimator, which is going to be defined as the log ratio probability of between the path probabilities, but only over the visible part of our trajectory. I mean, and these probabilities can be obtained because you just have to marginalize the total path probabilities over the hidden parts. We want to define this irreversibility estimator because it follows some nice properties. One is that it fulfills a fluctuation theorem by itself, an integral fluctuation theorem. And also that we know that you can show that the average of this irreversibility estimator is going to be a lower bound for the average total entropy production of the system. And it is known from previous work from Parrondo, Van der Broek, and so on. So now I'm going to jump in our results. Our result is that we find a fluctuation relation in the case of imperfect monitoring that is linking the stochastic entropy production of the system conditioned to a given visible record with the reversibility estimator in this way. And by just applying Jensen inequality for conditional expectations, you can find that the reversibility estimator is a lower bound for the conditional entropy production of the system at the level of single trajectories, because the reversibility estimator is defined from only one visible trajectory. Okay, at this point you can tell me, okay, this is a lower bound, but it can be, a bound for the average of something can be a but lower bound, for example. So we also derive some some bounds for the probability of overestimating the entropy production of the system with the reversibility estimator, and we find that the probability of overestimating the real entropy production of the system is exponentially unlikely. It means that the reversibility estimator is a really good bound for the stochastic entropy production of the system, and also we find some family of bounds for the underestimation of the entropy production that are quite complicated. So now these are the theoretical results. I want to show you more into detail with a particular example. I'm going to take again the example of a two-level system with driving in contact with single equilibrium reservoirs that have these Limlat operators, and here we have this delta S for the detailed balance. Okay, in this first plot you can see the fluctuation relation, but for different trajectories. One is in which we cannot see any jump. Other one is in which you have one jump and two jumps. As you can see, as you take sufficient number of trajectories, you always have a good convergence. Just checking the quality. And then here you have the tightness of the bound as a function of the efficiency. Here I'm supposing that both channels have the same efficiency. As you can see, the shorter is the trajectory, the better is the bound. And also, as you increase the efficiency, you will get that the stochastic entropy production, the reversibility estimator becomes more and more equal. And in the limit in which you have eta equal 1, the reversibility estimator is just the stochastic entropy production of the system, which is something that you can expect. Okay, now some extra comments about this is like everything that I have shown you can be formulated in the case in which you have only one thermal reservoir as just lower bounds for the heat that the system is dissipating, in which now we will have this effective entropy flow that is related with the reversibility estimator in this way. Remember that the change in the entropy of the system is just defined by the 2-point measurement scheme. And the second thing that I want you to comment is how we can obtain these results. I mean, every time we are deriving fluctuation theorems and all this kind of stuff, the result that we obtain is encoding how we define the reverse protocol. And in this case, if we want to have all these bounds for the irreversibility in the system for a given trajectory, it means that you have to be able to, in the time reverse process, not only to invert the time and the driving, also to change the efficiencies in the channels. I mean, imagine that if you have a process in which you cannot see any absorption, you have zero efficiency in this channel, it means that you, in the reverse protocol, you will need to have zero efficiency, but in emission. This can be seen as a experimental limit, I mean, an experimental problem, or also can be seen as a theoretical insight on what are the things that you need in order to define dissipation in this way in a real experimental setup. So up to this moment, this is all that I want to tell you about the first part, about about the inefficient detection. One is that we have derived a fluctuation relation that links entropy production and irreversibility and the imperfect detection. We can estimate dissipation from irreversibility for a single trajectory, and this is pretty nice. Also, we have derived some lower bounds. We have no overestimation of the entropy production of the system. And we have also bound underestimation of the entropy production. It can be applied for both imperfect and inefficient and partial detection setups. It can be used also to handle apparent unidirectional transitions, which is the case in which you cannot see one of the two channels. I mean, you can also you can only see, for example, jumps for absorption or for emission. And also, all that they have shown you can be applied for both quantum and classical jump processes, because the classical limit, in the classical jump processes, you will only have the jumps part. So it's going to be more easy. And some future work will be to extend this for diffuse trajectories and to have some applications in experiments. So now I want to pass to another different things. That is work that I have been doing during the more or less the last year, and it's about feedback, gambling, so martingale theory, and it's about stopping problems. What is a stopping problem? It's just a decision-making problem where we have to determine when we want to end a particular realization of a random process. I mean, this unstopping problem is defined by a stopping rule, which is the condition that we want the system to fulfill in order to stop the process. And the second is the stopping time. It is the time at which this condition is reached. And by definition, this stopping time, most of the time, is going to be a random variable. So this can be the analogy, for example, of a gambler that is playing a game, and he wants to invest some money, and he wants to gain some money back, and you have to guess when you want to end the process in order to not to lose a lot of money, or maybe to win some money. And also, this can be applied to stop some non-equilibrium process at an stochastic time. That's the case of this paper from Gonzalo et al. In 2021, in which they apply this to non-equilibrium steady states in order to derive some Maxwell-Demon-like fluctuation relations and inequalities. The main result of the paper is this fluctuation relation for the case of gambling, in which the demon is investing some work in a driving dissipative process, and he wants to get some free energy. And you want to stop the process in a way in which, on average, maybe you will win some free energy on some work. And this fluctuation relation implies a second law-like inequality for stopping times at stopping times, where now we don't have the normal second law, which will be the case in which we have a zero here. Now we have this second law with this delta, which is somehow a distinguishability between the probability distribution of the system at the stopping time in both the forward and the backward process. And this quantity here can be negative, meaning that the demon can win some work in some scenarios. And this is something that they see in an experiment in this paper. So now what is happening here? Okay, in this setup, what the demon is doing is he's monitoring the state of the system every time, measuring a quantity, for example, the work. And once we reach a certain threshold, he ends the process. Maybe you don't reach the threshold never, and you reach some time tau, and you end the process, or maybe you gain some work, and you also never stop the process, and maybe you start to lose a lot of work, I mean dissipate a lot of energy, and then the demon say, no, I don't want this, and he ends the trajectory very, very short. So this is what is known as a feedback control scenario, a very particular case of feedback control. And we can also, which is just I mean, it's just the case of the normal Maxwell demon, but in another way. So you can try to formulate this case, this problem by going from the way of information theory, like considering the demon also. I mean, trying to see what happens if you take into account, because here you're having that you are violating the second law, the normal second law, for example, in some way. So it's meaning that you are not taking into account, for example, the information that the demon is obtaining from the system because of the measurement. So we want to formulate this problem from the point of view of feedback control. Okay, just as a review of what is known in feedback control theory for thermodynamics, is that you have a system that is undergoing some stochastic dynamics, and then you have measurement outcomes. It can be one, or it can be a continuous measurement of the system, depending on whatever you want. And then you have a controller that just change external control parameter that has some effect on the dynamics of the system. I mean, you are measuring the system, and then you are changing some parameter in order to drive to stop or to do whatever you want in your system. And in this case, you have that the second law takes this from here. You have this fluctuation relation that now involves this quantity here that is a transfer entropy. And in the case of discrete feedback control, or the standard Maxwell demon, is just the mutual information between the measurement outcomes and the trajectory of your system. And by Jensen inequality, you will have this second law-like inequality here, where now you again can gain some energy. I mean, you can violate the second law, because this quantity here, if the transfer entropy flows in from the system to the measurement apparatus, you will have some like the illusion that you are winning some energy, you are generating some energy for free, which is the case of the standard Maxwell demon. So our goal here was to see now if we can formulate this setup for the case of stopping times and then compare with the gambling demon. I mean, just a competition between Maxwell demon and gambling demon, something like this. Okay, for this, now we have this particular scenario in which the measurement is at each time step. I see if I have fulfilled the condition or not. So the outcome is yes or not. And if I have a no, I mean, I don't do nothing in the system. I let the system evolve. And then if the answer is yes, I have reached the condition, so I have to stop. Very easy. So we have derived this fluctuation relation in this case here, where this is just an efficacy that you have to put because of the definition of the backward and forward trajectories. This quantity here is the Shannon entropy for the probability of the stopping time probability. And this fluctuation relation have this second law-like inequality associated with it, where now we have here also the efficacy and the average of the, well, I mean, this is the surprisal, sorry. This is the surprisal of the associated with the stopping time probability distribution, and this here is somehow the Shannon entropy of the stopping the process. I mean, just to disconnect your system from the bats and from the driving. Yeah, disconnection of everything. Yeah. What? No, because you also disconnect the Hamiltonian, you disconnect everything. It's just physically, yeah. Yeah. Yeah, now here for simplicity, I'm supposing that everything is classical in this part, in the feedback control part. Also, maybe in the quantum case, you will have some kind of this happening when you disconnect and you are in a superposition, maybe. But here I'm supposing that everything is classical. Okay, now up to the moment, this is what I have done with this. We have for these quantities here, the stopping times, we have two different lower bounds. So next step is to see what lower bound is better. I mean, it is maybe it's better to trying to estimate the entropy production of the system by the stochastic indistinguishability, or maybe the information that you obtain in the measurements are better to determine the dissipation of the system. And also, well, I have seen in some numerical experiments that that the gambling demon is better, meaning that here probably because of that you have to measure at every time step, you are obtaining a lot of information that is not useful. But also another thing interesting that we have to see is this thing here, because this term also is giving to us the cost of gambling, because in order to the demon to operate, you have to record the total trajectory, and then to start again, you have to erase his memory, and the cost of reset the demon is going to be this quantity here. So a possible a thing to see is that how this quantity here behaves with the shape of the probability distribution of the stopping times. In other words, how the condition, the stopping rule that you take affects this quantity here, because they have seen in this paper that the case in which you can win some work, it's related with the condition that you put for stopping. So it is interesting to see how these optimal stoppings here give you maybe how they relate with the cost of what is the cost of these optimal stoppings in some work. So I think that this is all. Thank you all for being here. And
So if anyone wants to ask anything, just raise your hand. Otherwise, I can perhaps start. So, so in the first part, how do you think this kind of relations could be applied to other types of trajectories, like diffusive trajectories? So do you think they will apply in the same way, or something different may come out?
I mean, I would say that it will apply in the same way, but the only difference is in the term of the noise, because in the diffusive trajectory you have something here that looks like more like a random white noise, and this here is a Poissonian noise. So probably I would say that the rest is more or less qualitatively the same. So I would say that the main difference between the diffusive and the jump cases will be the noise. But I mean, you will find something similar, I would say.
Okay. But in this case, so I mean here.
I mean, you're having more jumps in the case of the diffusive. In the case of the diffusive trajectories, you're having more jumps. Also, you are not seeing a lot of them, but you are having a lot of jumps. So probably I would expect that in this case, you will derive better bounds for the interpolation. Probably, I don't know.
Okay.
Better bounds, because you are losing information, but you have a lot of information from the system because you are having a lot of jumps. Maybe.
But they have a smaller effect on
Yeah.
your system.
Yeah, okay. Also. Yeah. That's yeah. Yeah, I mean, yeah, it probably compensates. Yeah. I don't know.
Thank you. One question about this hidden absorption and hidden emission. I didn't, maybe you said this, but do you have to assume any specific properties of the hidden data? Like statistically, do you have to be like uncorrelated? Or, I mean, how do you put in your formulas the fact that you are missing some jumps?
The fact that I'm missing some jumps. Okay, well, the fact that I'm missing some jumps is here. I mean, the equation that is defining the system, the evolution of the system, is taking into account that I am not seeing some jumps with a given efficacy.
But is that like at random? I mean, which jump?
It's random because, but it's random, but it's random in a way that the ideal evolution of the system is fulfilling local detail balance, for
Okay.
example.
So it's not that okay.
I mean, it's random, but in a in a thermodynamic way. I don't know. I am the process. I know that the process that is running on the background is a thermodynamic process, and the jumps are produced by a reservoir that is in thermal
I mean,
equilibrium.
I'm not a quantum person, so excuse me if I'm asking these kind of questions. But so if you have a record of the jumps,
Yeah.
like a I don't know, like a Poisson process or something like
Okay.
this. So is it fine to just remove them doing like a Bernoulli trial, like at random? That process would satisfy your thermodynamic constraints,
Oh. I mean,
or do you
you're
have to
asking
make
me
something more careful?
if I can guess from a record if it is a trajectory that has hidden jumps or not. Well,
Yeah, that could be a way of saying it. Or maybe, I mean,
I mean,
how do you?
the answer is no, because, for example, imagine that you give me I would say no. I mean, it's a good question, it's an interesting question, but I will tell you that, for example, you give me like a visible trajectory. Well, probably I can say if the process that is in the background is a thermodynamic process, maybe from the local detail balance with the I mean, I can see that your jumps are not fulfilling local detail balance. I think maybe I can tell you, oof, you are losing something. But but maybe also these jumps here are like having local detail balance for another reservoir.
I mean, I'm asking this because if I am a kind of demon, I could always hide jumps in a certain way that I can ruin up your statistics, right?
Okay.
That I would change totally the apparent
Yeah,
reversible properties. So I guess that in order for the true irreversibility to be maintained, the way you hide the jumps should fulfill some certain randomness criteria.
no, I think no. I mean, okay. Now I think that I understand. You're meaning that this is the visible trajectory and you are a demon, no? And then you say, okay, I'm going to like if you remove jumps from here, I can still estimate dissipation from the system. If you put jumps here, I mean, I cannot.
But that's my point. If you remove jumps from there, my question is, does your formalism, the way you are retrieving, do you have to assume that the way you have removed the jumps
I don't
have a certain property? Because if I remove,
don't think so. I don't think so because that very good question. But we're in the case in which you are removing jumps from here. I mean, if you put jumps, I am wasted. But if you remove jumps from here, I mean, I don't have to suppose anything because at the end, in the space, I mean, my results fulfills for every possible trajectory. So if you remove jumps from here, it also will coincide with a possible visible trajectory. I mean, from the infinite space of possible trajectories. So I can still estimate the dissipation of the system.
Thank you.
Yeah. Probably if I have a lot of jumps here and you remove like the half of them, I will estimate the reversibility in maybe worse than the case in which I have more jumps because I have less information. But I can always bound the reversibility.
I mean, it's like, so removing jumps can be seen as adding noise to the system, right?
Yeah.
Some kind of, I don't know, dichotomous noise or something like this. So maybe the noise has to have some properties, be white or.
No, maybe in the case of diffusive, but in this case of just Poissonian jumps, no. Because, for example, what would be the case is that, for example, for the trajectory with a lot of jumps, my bound would look like this. Then you remove some jumps and I have a bound like this, like less tight, but still a bound. And then if you remove like all the jumps, I can still like bound the irreducibility. You will only change like the tightness of the bound, but the fluctuation relation and everything is going to be fulfilled. Yeah. Yeah. I mean, the thing that you need is just to have local detail balance on the background, because if you don't have local detail balance on the background, you cannot define the stochastic control production of the system. So.
Thanks.
Any other question or comment? Otherwise, we recap.